poll you guys. I know that you got these cards yesterday. I'm kind of known as the cards guy, so get used to this. You're going to be using these quite a bit. Get them out. Hopefully you didn't forget them. You're going to need to fold them so that you can vote with them. I actually want to run through some rules. If you don't have your cards, maybe you forgot them, maybe you lost them, it's okay. They're almost free to create. And we can bring you more if you put your hand up. Be happy to bring you one. Just one up here, a couple folks. I just want to kind of gauge a few things. In listening to you guys ask questions, Andy did something really important in talking to you about the population of students that you're going to be working with. It's not as though we work with just one population. They're all future versions of us. In fact, it's a very small fraction of the folks you're going to be working with. And I know that you guys come from a very diverse set of backgrounds, and I kind of want to gauge that somehow. So I'm going to make up a question to vote on, but I have to kind of give you the rules of voting first. First rule is simultaneous. Please don't vote until I count to 3. And the second rule of voting is anonymous. Hold your vote right here. Nowhere else, not up here so somebody else can see it, but just right here, and not until I count to 3. And I'm going to make up a scale. I want you to kind of vote on your prior preparation before, before even graduate school. Let's just talk about, what we would have called high school, or while you were a teenager, and then your undergrad preparation. Where was that done? Let's let A represent in the U.S. and B represent elsewhere. I'm just a little curious. Let's vote on 3. 1.
Sorry, can you?
Yeah, A represents that you did your high school and undergraduate preparation in college outside of the U.S. Oh, sorry, A meant in the U.S., B is outside the U.S. Thank you for helping me. Let's vote on 3. 1, 2, 3. Okay, it's interesting. It's a little more than a 50-50 mix towards people that have done their careers. You can put your votes down outside of the U.S. I think there were a lot of interesting questions in Andy's first session. Things like, hey, doesn't this make it so that the really talented, if we will, or high-achieving students they run out of stuff to do quickly? No, it turns out if you're doing things that are intellectually engaging and really conceptually challenging and have a lot of context around them that everybody has to really work through in a pretty intellectually sophisticated way, then even those students that you believe are the best students are also challenged. What we do find, though, that is if problems tend to result around a set of equations over and over that are other examples of the same thing over and over, those students that start to understand, hey, you're just solving the same problem over and over in different applications, they do become sometimes unchallenged by that. So think about, as you see many different examples, and you are going to see a lot of different examples of types of an engaging curriculum, know that one of the things that most of them are pointing towards is getting people to engage in some kind of discourse with each other. And that is really the currency, if you will, of what I want to show you today, is how could I show you how to create a learner-centered classroom. I'm going to use astronomy as my vehicle just because I'm an astronomer. I'm here as a representative of the American Astronomical Society. And I just want to know, let's try this again. A is, I know I'll be teaching astronomy. B is, I might, I'm not sure. And C is, I don't believe that I'll ever be teaching astronomy. Let's vote on that. Let's vote on 3. 1, 2, 3. Yeah, those of you voting C are mostly wrong. Just letting you know. Many times you folks all think, I'll never teach astronomy, and then your college is like, hey, could you, we need somebody, just so you know. The other thing is, why wouldn't you? You're a physicist looking for really, really cool problems that show where we actually are as a discipline in understanding the natural world. And astronomy is your other science that you could draw from that brings some of the most amazing kinematics problems, dynamics problems, E&M problems, quantum problems into your classroom in a way people actually like. Throw that out there. Okay, let's go ahead and get started. So I work at the University of Arizona. I just want to throw this up because I'm going to talk about a lot of different things that we work on. It's all part of a very large national collaborative that's been funded by both the National Science Foundation and the NSF, and it involves a very large group of people, and this is a pretty incomplete list because it's actually quite old, and I just want to point out Richard Schnee here. He's actually should be on this list because he's actually contributed to some of the research that I'm going to talk about today. This is work that's been done in all types of colleges, all over the country, many different institutions. So I just want to bring up that sometimes folks are going to talk about research that's been done on their curriculum at their school in several semesters or years with a population that's at that school. I want to make sure that you realize that the materials that I'm going to be demonstrating in this workshop session and in the follow-up session that we do after this have been tried at all sorts of different kinds of universities and shown to work. Large classes, small classes, community colleges, four-year institutions. I think Andy said the same thing earlier, and I just want to kind of reiterate that it isn't deterministic on where you're at or how well prepared your students might be necessarily. or what size school you're at. It's about you. There's a huge amount of the message that I'm going to try to provide here that really talks about your implementation, your ability to create a constructive and productive classroom environment, knowing that there are many tools you can draw from. So I'm going to try to demonstrate those tools. I'll give you a couple take-home messages. Interactive teaching strategies, the things that we're all going to be demonstrating, have been shown to work. I can show you data on each of the different strategies that I'll be demonstrating while I'm here today. They each have their own research base done at multiple institutions to illustrate that they promote learning gains higher than traditional instruction. I have found that that isn't as successful as I had hoped it would be, appealing to you with data. So I want to demonstrate those kinds of activities instead of showing you data that they work. But I will say that we have data that demonstrates they work for all students, high and low achieving students, strong and weak math backgrounds, all socioeconomic groups, both genders, that positive correlation between the use of interactive learning strategies and all of those different characteristics are shown. So I'd like us to kind of try to think about moving beyond skepticism about, I'm not sure that the good student, or really, what about this small group that I'm worried about? Okay, start thinking more about, if you would, your own teaching and your practice as a teacher, because that's going to be the thing that really affects whether or not any of these strategies work in your classroom. So the quality of implementation or the fidelity of implementation becomes critical. We run workshops as part of the Center for Astronomy Education all over the US. They're often held at national meetings of the American Astronomical Society. They're also held at colleges around the country. And I just bring this up to say, if you're taking your teaching seriously as a thing you would like to be an expert at, this is just a beginning. You might want to think about coming to another workshop. We offer them. They're free. They're much more intense in some ways than the workshops that we're doing here. They're 2 days long. They're a boot camp of how to teach. So please feel free to come join us. Again, they're held all over the country. There's a schedule on the website. You can get a card from me. I'm sure there's email correspondence that will take place for any of you that want to come to the meeting with myself or with Gina. One click. There we go. I'd like to try, for the time I have left, to do as much interactive teaching as possible, because I believe that many of you, especially of you that were voting B, may never have seen an example of interactive teaching in the classroom. And so I actually want to try to just spend my time demonstrating it as much as I can while also asking you to become a part of it. So this is going to be socially a little different for many of you than what you think of a classroom environment. And I'm going to demonstrate as many different types of activities as I can. But there's a message that you need to hear from me, and that is you're not expected to do all of the things that I'm going to demonstrate to be successful. Almost any one of the techniques that you're going to be shown over the next day from myself and others, if you just tried that, you would be a step more successful than what you might be from just traditional instructional techniques. So find the thing you kind of like. Find the thing you're like, I can imagine doing that. That makes sense for me, and I kind of think about how I teach already maps into that pretty well, and go for that, and go for it for a while, and get good at it, and then add something to your toolkit. At this point, as many of you were demonstrating from the just-in-time teaching, you think about your teaching as a way of, or you think about how to teach based on how you were taught. And so at some level, you have one tool, hammer. And you're encountering many different types of fasteners and attaching things and hitting them with your hammer, because that's what you got. And I'm going to try to show you many different tools that aren't hammer. But it's up to you to decide if you see how to use that as something meaningful to you, and I'm going to do my best to demonstrate it. Know that I also am a weird person. My teaching persona is kind of odd. I've been described as being a tough coach game show host. And that's not something all of you would like to do or should think that you have to do to be successful. That's another thing I want to bring up. You do have to be your inner teacher, which is sort of like the boss of the classroom at some level. And for some of you, that's not hard. For others of you, it is more of a challenge to have that happen and maintain a healthy relationship with your students. So keep that in mind. I'm going to move forward a little bit here. So as part of this slide, I require you to play along. I'm going to start lecturing, and I'm going to pause. And at some point, you're going to know the word that I would have said if I had kept lecturing and not paused. All I ask is that you fill it in. This is a form of interactive lecturing, which requires you to, in unison, decide whether or not you're following along. And if you can't fill in the blank, or you use a different word than everybody else, you're going to suddenly know in real time through formative feedback right now whether you're on board or not. Good luck. It's not going to be hard. This is a warm-up, okay? Gosh, your clicker is finicky, Gina. You live on the planet. Let's try that again. You live on the planet. That was almost all of you. Really? This is the one I expect everybody to get right. All right, so we're going to keep doing this until all of you say a word together. You live on the planet? Earth. Oh, thank God. Okay. You're orbiting the sun, which is a star. Okay, and it's a star that we call the sun. Just checking. Okay. All the planets and dirt and debris and asteroids and comets, all that, almost nothing, like 1% or less of everything that's orbiting around the sun, and the sun is known as a solar system. There are billions, in fact, there's hundreds of billions of those in the galaxy. Ours is known as the Milky Way galaxy. Okay, and there are hundreds of billions of these in a larger structure known as the universe. And we call ours the universe. Yeah. Okay. All right. So that's just warming up. Okay. I lecture in my class using an interactive technique that requires students to be part of the lecture, and they find that this is very helpful for them to also know what's important as we move to more sophisticated things than this. When I pause, I'm pausing on things that are going to be on the test, that are going to be in the homework. I'm forecasting exactly what I feel is important that you know by doing this in class. And my students don't rush up to me every week like, I just can't organize it. I don't even know what to know. What do I need to know for the test? I'm forecasting it all day long in class, and they're right along with me. So it's just an example of interactive lecturing. I work in probably one of the worst classrooms in the country. That's my classroom. It seats 2,500 when the show like Wicked's in town. We've converted our Performing Arts Center into a classroom. It's terrible. I'm not bragging, it's terrible, okay? But it's a good challenge to figure out what are the limits for these active engagement strategies. What can be done when you're asked to teach it for 1,000, let's say? So we've taught classes as big as 1,000. I average around 700 to 800. This is half of the class. It's kind of shady in here because the class is dark. It was never intended to be a classroom. It's the Performing Arts Center. So even to get this picture, you have to leave your camera lens open for a while, which means everybody turns into a smear. I had to stand as still as I could to get the picture. These are TAs. This is a picture of my class voting with cards. So maybe you haven't realized that you have an E choice. E is the white choice. So you see that in here there's a bunch of white and some pink or red in this. So my class votes every day with these. I am not anti-clicker as much as I am pro-cards. These things never break. You never need to set up a polling session if you don't want to. You don't have to have any kind of sophisticated software at all to run it. No technology is necessary. Students can download new ones off of the website of your class anytime they lose theirs or it runs out of ink, whatever the problem might be. And you in real time know exactly what everybody's voting every time. And they know, you know what they're voting in class every time. And suddenly they want to be right at a whole new level. And no points were involved, and you're not keeping track of anything. I think one of the biggest obstacles to implementing instructional strategies for faculty members that are trying to get tenure is, can you please just make it easy for me? It doesn't get much easier than this to do polling in the classroom like clickers do. The only thing you're losing is some data, if you will, on students' responses that you might give them points for a quiz. But we have seen that sometimes the conversations students have when there's points on the line are very different. They're like, dude, what's the answer? Come on, I want to get these points. I need these points. Rather than talking about the physics that you wish they would be talking about. So just keep that in mind. There's a trade-off. Then you have to do grading, and you know they're going to nitpick over every single point if there's any points involved at all. And you'll see people with 3 clickers and things like that. So just keep that in mind. Cards are really valuable to do almost everything clickers do, and more in some ways in terms of what you know about what everybody's voting in real time. So I'll just give you another little picture of that. My class is primarily taught by a group of undergrads that aren't science majors. I teach gen ed astronomy, which means most of the students in my class won't be science majors. They're education majors. They're political science majors. There are citizenry. And you know what? The truth is, so is your class. We're both teaching a class that is future citizens. So I want you to keep that in mind. You're not teaching future versions of yourself. Little physicists running around in there all day long, okay? These folks teach my huge class. There's 10 of them on average in a semester. They make $10 an hour, and they are better teachers than I am and my grad students. They got an A. I never got an A in my class. I have no idea what it takes to get an A in my class. I think I know. They really know. And when my students are stuck and a hand goes up because two students are engaged in a discussion and they need some help, the metaphors, language, analogies these students use are more profitable to my students than the ones I likely am going to come up with or my grad students. Keep that in mind. For those of you that are thinking and struggling, like, how am I going to implement all these strategies? I'm going to need some help. It's in your class probably right now. So if you want to talk about how to develop a learner assistant program or a PTA or peer teaching assistant program like we run, please feel free to talk to me. It's a really, really, really valuable thing. And I attribute them to the large gains that our students have in terms of pre and post testing. Because they do the majority of the teaching in my class. They hold all of the office hours. They're amazing. So when you wonder, how could you possibly teach a class of 1,000? I have a small army of former students who come back in droves wanting to teach this class. We have to run interviews and only let some of them in. So it's a very popular thing for them. It's a picture of my class voting, and I just want to show you some. This is zoomed in on a small part of the class, right? This is bigger than many of your classes are, judging by the fact that many of you said you teach 25. What's weird is you start to learn things when you have a class this big you'd never know otherwise. Like, what if you have a group of students that are the size of a class that are all wrong? Imagine them clicking and not knowing where anybody is in the classroom, or even if you did know where they were in the classroom and they're all wrong. We used to believe that half the class had to be right before having them talk to each other could ever be profitable, right? Because then they're really just going to exchange disinformation and never get anywhere. This is one of those rare cases in the universe where two wrongs makes a right. These folks talking to each other don't often stay wrong, which is really interesting. This is a picture of them talking. So if you see people's faces that are smeared and you see gesturing, that's because they're reasoning out the problem and talking to each other, and the camera has to stay open. So sitting still is the thing you got to be worried about. Anybody who isn't smeared at all, that's a troublemaker. Okay, so this is the post vote. What's the right color answer? Green. It's pretty quick. Your brain's quick at this. It can do this quickly, and we've done tests with three of us looking at photographs of my class and counting, and also making marks in real time in the class and looking. And we're within 5% in our own estimates as 3 people, estimating what the highest distribution of votes are. And that group of people that were mostly wrong aren't all wrong anymore. That's the interesting thing. Having individuals talk to each other about something that engages them intellectually and forces them to really commit to a conversation. When you're holding the vote in front of your face, it's awfully hard to lie about what you just voted. It's there. That's what I voted. And so I'm going to try to show you how to engage at that level in the classroom. So I use this quote because many of you are the best learners. You got your PhD. You came from amazing backgrounds and preparations. But sometimes we're the worst teachers. We can't imagine what they're struggling with. And we think this is the coolest thing ever. Right? We're like, oh, God, I love this. It's my natural language. I love this. Like some of you are currently looking for your favorite part of what's going on up here, right? You're so addicted to this. This isn't it, you guys. We tend to rely too heavily on mathematics, and that is a language, and the only way we understand how to communicate and help people learn and understand and think. And our students aren't native speakers, if you will, often. And they're struggling just to understand the representations at all, let alone develop a mental model that lets them account for physical phenomenon, make predictions, explain and extrapolate ideas, and we over-teach, if you will, how to grind through symbolic representations over and over and over and over and over and over and over. And what we have found in the research is when you help them develop their physical intuition, their critical reasoning ability, their ability to abstract to new ideas and transfer knowledge from one application to another, independent of solving arithmetic problems, they're also often able to solve the arithmetic problems better. So I just want to make that point, okay? This isn't what you actually believe the culture of physics is either. You're an educator, which means you're trying to transfer an entire culture of information from your way of knowing to a whole other group of people, and that's all we tend to show them. As if that's what we do for a living. Like we all go back to our offices later and grind out problems all day long. That's what a physicist is. If that's all you ever show them in class, what did you actually show them about your discipline that should help them understand its relevance in society or their future work? Keep that in mind. So I'm going to try to go a little forward. And I think I'll just save all the data for, yeah? I'm going to skip all the data. I know that you folks don't have often a rich background in astronomy. I'm going to use astronomy in here and in the breakout section as the topic that I'm going to teach you about. Keep this in mind. These are all ideas and examples from the classroom that I actually use in my Gen Ed freshman level introductory astronomy course, so be at ease. You're okay. And the other thing I want to say is this isn't about whether or not you're right about the astronomy. I'm going to try to model a whole bunch of different teaching practices. and I'm going to talk about my implementation of those teaching practices. I'm going to try to tell you why I'm doing the things I'm doing and how it helps motivate students to engage at a deeper level. And you're going to keep trying to be right about the astronomy. Stop it. Okay? It doesn't matter. Stop trying to be right about the astronomy. I know it won't work, but I have to say it. Got a quick question for you. Talk to your neighbor. You got about 30 seconds. What are each of these? 29, 28, 27. Okay. Time. Let's just try it out loud, shall we? This is a solar system. Excellent. Okay. Which of these, I got another question for you. Don't talk to your neighbor. Okay, you're still trying to be right. I can tell by your behavior. Let's talk about a few things I did. Did you notice when I threw the first question up, did I read anything to you? Did I do anything, or did I just throw you right at a question? Chucked you right at it. No instructions, no big framing around it. All I said is, here you go. And the other thing I did was I gave you a time signature. And then, did you notice what I did? It's okay to talk to me. It's okay. Say again? I counted down. 29, 28, and the volume in this room went up immediately. You're like, oh, he's serious. Yeah, I'm serious. Part of your job is to let them know if their behavior is what you were expecting. And finding techniques to do that is what I'm trying to show you right now. Giving people an amount of time is critical. Otherwise, they will consume your class and do nothing for it. Holding them accountable to that amount of time and letting them know you're serious, like counting backwards. Simple thing you can do. You don't have to be as aggressive as I was. You go, hey, you have 30 seconds. 29, 28. And they'll still start talking right away, okay? I also have been framing things like, don't talk to your neighbor. That makes you kind of already accountable to the level like, damn it, okay, I'll pay attention for me. These little cues, cumulatively, all add up to make a class engage at a much deeper level and work harder and work together more and engage in more robust conversations. And that, again, is the currency of my class, is a conversation, a rich conversation where I'm trying to convince you I'm right. And I'll talk about that, how you can evoke that behavior. So I am going to go to the next question, and I'll just say, I have a question for you that I'll be asking you to vote on. Please don't talk to your neighbor. Are you ready? Are you ready? Okay, turns out that's not even the right question. You don't actually want to know who's ready. You actually want to know who isn't ready. And whenever you ask your students, are you ready? You're getting the wrong piece of information. The question you really want to ask is, does anyone need more time? Ask if anyone needs more time. Don't ask, are you ready? And in asking if anyone needs more time, if even one person mumbles yes, there are many people that wished they would have said yes to that they are answering for. So take that seriously. My rule is to just go back to the question and count to 10. And notice where I was looking. Was I looking at you guys while this question was being answered? You guys are awfully quiet. Was I looking at you folks while this question was being answered? Where was I looking? At the question. For your students, that implies this is the important thing. You may even see me gesture like I'm still solving the question myself and reasoning through it. You'll see students going, oh, I can do that? Okay, I'll start. Yeah, all right. Remember, you're trying to help facilitate their thinking, not look at them and like, what are you guys doing? Remember what Annie said earlier, like you only have a limited window to develop a relationship with them, okay? So let's vote on 3. Let's vote on 3. 1, 2, 3. Cool. All right, turn to your neighbor, convince them that you're right. Well, pause. Shh. I need you to hear this whole phrase because every word matters. We've actually done research on this. Turn to your neighbor and convince them that you are right. Just because you have the same answer does not mean you're right. So make sure you explain your reasoning. Then an amount of time, and I always say 30 seconds. I don't actually know how much time I'm going to give. And then a prompt to universally put you all into the same mode. That prompt, go. Now I'm going to say all those words because they have meaning. When you are operating at the convincing level, you're at the deepest Bloom's level, if you will, of active engagement. When you and your significant other are in an argument about something and you're trying to convince them that you're right, you bring every historical thing in the world to bear in that argument. That's the level I want my students arguing for themselves and advocating for their answer. Convince them that you're right. The other thing that happened when I said, turn to your neighbor and convince them that you're right, your brain heard you were right. You believe your answer at a whole new level. Like you just said, I was right. Totally just said, I'm holding it right here, I'm right. Okay, so just keep that in mind. That phrasing has a very particular discourse management to it. So I'm going to say the phrase again. Put your votes up. And don't change them if you've thought differently. Turn to your neighbor and convince them that you're right. Just because you have the same answer doesn't mean you're right. You got about 30 seconds. Go. 29. 28. Time. Remember, I'm not actually trying to teach you any astronomy, and I know some of you are like, God damn, I want to know. Yeah, you want to know. Pause. Some of you can't even stop. It's okay. Shh, please. Okay, being right about the astronomy doesn't matter in here. But notice that I haven't actually even been lecturing to you about anything. I've been using questions to promote a set of ideas that you're talking about. And it doesn't take that much time because I'm spending most of my time talking about doing it, not even doing it. So just keep that in mind. Let's vote again.
Wait, I have a question.
Sure.
This is about your presentation.
Yes.
The first time we put it up there, you said the word excellent. Did that have some meaning?
I'm sorry, the first time what happened?
When we all flipped up our cards, you said excellent, like you were happy about something.
I will say all sorts of things to not let you know how well you're doing. But at some point, I will give you a prompt that lets you know how well you did, and that's coming.
As a group.
Yes, yes. Great question. Great question.
Is there a correct answer?
Maybe. Let's try a vote first. Let's try a vote first. Let's vote on 3. 1, 2, 3. Okay. By the way, you did pretty damn good. The right answer? D. There you go. When I see 70 and above, all with the same and correct answer, I let my students know at the start of class, hey, if I say that to you, hey, by the way, nice job, that means you're almost all right. And I'm going to ask you to say your letter out loud. Be confident. Just say it. That's the bar graph. And if you're busy going D, or you're the one, unfortunately, next to that person going C, you just learned something about yourself and your answer. And I didn't have to show it to you. You're the source of the right answer. Okay?
That's a pretty ambiguous question. I mean, I didn't understand the meaning, actually, of this question.
Nitpicking questions will be at the bar later. I'm just demonstrating something. I made this up on the plane on the way here just for you guys. And it has a particular purpose. Are you in the Milky Way galaxy?
Yes.
Can you take a picture of the outside of your body while you're in it?
No.
You're in that galaxy. Do you know how far away from that galaxy you would have to be able to take that picture? Image. So was it the problem with image? Should I say photograph? And then we'd be okay. Oh, okay, let's change it to photograph so you can all have the... I'm moving on. Nitpicking the astronomy. Thank you for the suggestion, though. I will change that. That's a very good suggestion. Never try brand new questions with this group, ever. No. All right, anyway. So this is an image, photograph, of what we actually see when we look into the plane of the Milky Way galaxy at the visible wavelength part of the spectrum. And these are images of part of the plane of the Milky Way galaxy that we see when we look at many different wavelengths, and we get very different information from it. This has led us to be able to ask unbelievably, really important questions of the universe, this multi-wavelength approach and what we've learned about what's possible to see. So in these are lots of these. Yes or no? Yeah, billions of them. So could we find them has become one of the great pursuits in astronomy. And if so, what characteristics do they have? Is ours different? Could there be ones out there like Earth? And could we even detect, if there was something on its surface that was life, in our signal of the planet itself? Becomes where we are at the cutting edge of astronomy. And bringing that into the classroom is a valuable thing. So this is a table of other extrasolar planet systems that we've found. It's even incomplete. We're up to thousands now. And these are all relatively old ones at today's standards. And I just want to bring you to a set of information. This is distance on the horizontal axis. and you live on Earth, and I'm just going to give you a unit, the Astronomical Unit, or AU. Astronomical Unit, AU. Earth lives at 1 AU. Yeah, we defined it. We're 1 AU away. So here's Earth's distance. Look at all of these planets closer to their star than Earth. And if you could see the little label that's here, they're in terms of masses of Jupiter. Incredibly massive planets, very close to their star, all the way out to as far out as almost Mars. So I'm just showing this as a set of data. Some of you are starting to want to ask questions about it. No, we're going to move on. Here we go. Here's a cartoon of an extrasolar planet system with a star and a planet drawn. It's terrible. Look at how close that planet is, and it's terrible. Anyway, I want to teach you how we find these planets in here and in the breakout session. So I'm going to do this quickly because you guys have PhDs in physics, so you got all this. Here's a picture that is often used in textbooks to try to represent this, and I'm going to walk through this with you. This is the sun. Cool. I'm going to go with star just for now. Okay, this is the star. Planet. Now, we actually find the planet by detecting something about the star. We detect its light being shifted. Yeah, it is moving in an orbit about the center of mass, as is the planet. And as the star moves, there are times, you have to imagine yourself being Earth, there are times where that star is moving towards, and other times where it's moving away. And when the star is moving toward, the spectrum of light you will receive from me will be blue shifted. And then when it's moving away, it will be red shifted. So by watching the signal, if you will, of the star over a long period of time, you can watch it go from being blue, not shifted at all,
Not shifted at all. Blue.
Excellent. Now, if you were looking at the star's signature, the light from that star, its spectrum, and you saw that it was blue shifted, you'd go, oh, that star's moving. What direction is the planet moving? Okay, so a little bit of a sign convention here that I think we all need to agree on. This is a graph of data of the star's motion inferred from its Doppler shift. And I just want you to realize that when we're talking about a positive velocity, that corresponds when the star was moving toward or away. Away. Just like every coordinate system you've ever taught your students. There's an origin, and as things move away from it, its displacement is positive, and therefore the velocity is positive. So this is the motion when the star's light was blue or red shifted. Blue or red shifted? Okay, I can tell you're already in disagreement. This is awesome. Okay, but it is definitely moving away. 50 plus, moving away. 50 minus, moving. So negative velocities correspond with motion toward. Okay. So here's another rule to start incorporating into your model. You've got blue shift, red shift, motion towards, motion away. I want you to realize that the amount that the light is Doppler shifted is related to this expression of the planet's mass, the star's mass, and the distance they are apart from each other. That is the relationship. So I want you to do a little bit of voting with me. I want to develop this model a little bit. A or B? Which of these two cases, and let sizes indicate masses for those of you like, are you trying to play a trick on me here? Not. These are the same size and mass. These are different, and their sizes are related to their masses. Vote. Which one would produce the greatest Doppler shift? Let's vote on 3. Which would produce the greatest Doppler shift? 1, 2. Yes, distances are the same. 3. Excellent. The right answer is B. Okay, I have one more choice for you. These are the same masses. Let's vote on 3. Which of these would produce the greatest Doppler shift? 1, 2, 3. Well done. The right answer? B. Okay. So there's a physical relationship that you can carry forward that we can reason with to infer information about different systems. Maybe we should look at a system. Now, here's 2 pictures. There's version A and version B here of 2 different extrasolar planet systems. I'd like you to vote. A is only A, B is only B, and C is either one. Could you detect the planet in these systems? I could detect them both. That's choice C. I can only detect A, vote A. I can only detect it in B, vote B. Let's vote on 3. You're the observer. That's your line of sight. I don't know why physicists need every little nuance spelled out, or else. I saw nothing more than this just a second ago. Let's vote on 3. 1, 2, 3. Pretty good. The right answer? B. This is never going to be moving toward or away from you. So its light will never be Doppler shifted. I just wanted to make sure you saw that that orientation was possible. It's okay. So I got another question for you. Do you notice that I really just have a lot of questions? Yeah. I'm lecturing, sort of. But you're doing all the work. I've just chunked it into pieces that allow you to move forward with me in sizes that you can digest each step of the way. And now we're getting down to that thing I asked on purpose a moment ago that you weren't all in agreement about, that you've been thinking about, wondering if another question was coming, and here it is. I have another question for you. Okay, let's vote on 3. 1, 2, 3. Oh, nice work. The right answer? B. Okay, I am going to now make this hard. This was all the easy part. This was all just kind of making sure that you had a couple of good pieces of reasoning tools to work with. You need some actual applications that matter. And in your class, you will spend a great deal of time deriving formulas that no one will ever derive again. You spend a great deal of time telling historical perspectives or giving background about every simple part of or complex part of every new piece of information you're dealing with, every caveat, everything. You will unpack your entire luggage in front of them and not have asked them anything. Think about how useful it could be to only unpack certain parts and check with them on their level of understanding as you're unpacking each part. And as you build cases and nuances and rules and assumptions, you have something that epitomizes each of those things that you're asking them to vote on and talk about. I'm trying to show you how you might be able to do that through anything that you teach. I teach very sophisticated ideas about the expansion of the universe and use these same tools. And I'm going to show you how it can get harder. Actually, I'm going to skip that slide and go to this one. Oh, I have to let you in on a vote. This is a legitimate vote that you should always use in case you need to. I don't know. Totally legit. If you ever find yourself being asked one of these questions, you're like, I don't know. This is a really legit vote. Please use it. I need to know that. You need to feel free to express that. Please don't talk to your neighbor. Do you need more time? Let's vote on 3. 1, you guys don't seem so happy anymore. 2, hold on. I'll take questions in just a moment. Let's vote first, okay? If you don't like the question, you're like, I don't like the question. It's totally appropriate. This is another way to express that. Let's vote on 3. 1, 2, 3. Excellent. Actually, wait. You know what? Nice job. Right answer? B. Time in years with numbers. Oh no, yeah. Physicists hate that. I'm sure this is 20 miles per hour, and I meant this one to be kiloparsecs per second. Physicists love this kind of stuff. Like, hey. Okay. They're the same. Sorry, they're the same. Yeah. And then I'm going to go to another one. I would not deny that as a valid point, that everybody made the same assumption about. I have one more for you. Are the letters too small? Okay. I got back of the room saying no, so I feel okay.
This is our perspective again.
Yeah. well, any best possible perspective. John.
No, you said the Earth is the Earth.
Sure, I'm the Earth. If it helps, I'm the Earth. Please don't talk to your neighbor yet. You need to know if you know this by yourself. The first vote is really important to do by themselves. Even if you're in the back of the class and I can hear you all the way up here, it's still really important. Okay, do you need more time? No. Let's vote on 3. Let's vote on 3. 1, 2, 3. Oh, finally. All right, turn to your neighbor. Convince them that you're right. Just because you have the same answer doesn't mean you're right. You got about 30 seconds. Go.
C is the greatest, so it has the biggest motion, so it has the biggest
Yeah, I didn't notice before now that someone asked the star for A, but it shouldn't matter.
So far away doesn't but the star in A doesn't shift that much, so the Doppler shift is going to be really minor compared to
Yeah,
like
that's what I
C
say. I don't
or
think
B.
Time. Let's vote again on 3. I know some of you are like, really? That's all you're going to give me to talk? Yeah, that's it. Let's vote again on 3. 1, 2, 3. Okay, that's about 90%. Right answer? B. But there are some other votes going on out there, and I know some of you are going to, I'm going to wrap up my talking to you about this in just a couple minutes, and we can ask questions and whatnot. I'm just trying to show you as much of this as I can. Got a little bit more to go. These are those same graphs. These are those same representations, drawings. I would like you to try to match them. Which graph goes? Yeah, I just heard it. Oh, Jesus. Damn. Do you know how early it is? You've got more than 30 seconds. Don't even bother trying to do this by yourself. Work with your partner. You got about a minute or so. Go.
I'm going to say
What do you want, like B to F, A to...
If you need help, please raise your hand.
No, we're just guessing. Probably that's just exactly A to E, B to F. Really? Yes, because it looks like a F is the largest. F. That's the E, F, G, H, right? Oh, okay. They try to match each one. Yeah, I know. So F is B with F, A with E. From this you can have it. So the smallest, so E is the smallest. No, I think way too slow. Radio velocity comes faster, no, it's a star because you detect light from the star. Right? So the radial velocity is the actual velocity.
Pause, time out. I just want to say, nice job, you guys. We've been doing these workshops here at the New Faculty Workshop Series for a long time, and it isn't always the case that people are willing to talk to each other. And it's almost like, for whatever reason, you guys are pretty open to it. Like I just said, talk to your neighbor about it. And I literally only saw a couple people not immediately start talking to each other. And as I walked around, I didn't see anybody not talking to somebody else about their answer. And that's pretty cool to see. I mean, as faculty members, doing that is a pretty important part of understanding why this might be valuable. Are you engaged in a discussion about astrophysics right now? Yeah. And you're talking about velocity, period, distance apart, force, amount of Doppler shift. You're having a full conversation about everything I want you to be talking about. All I had to do was give you a context rich enough that it embodied all of those ideas. And I didn't lecture about this very much at all. We've been in an interactive classroom for about 15 minutes right now. And mostly what I've been doing is asking you questions and making you talk to each other or vote, holding you accountable and giving you real-time feedback over and over about your developmental state and your understanding of this content. And right now, you're sort of in the medium depth of the pond. It's going to go one deeper in just a second here. So I just wanted to check in and let you know, nice job. Because I think sometimes faculty members check out right about here, and you guys didn't, and I appreciate that. So I'm going to give you about another 20 seconds. Go.
I think the amplitude is here. So I guess the smallest is H. Smallest is largest D. So I guess smallest A and D. Okay, so looks A corresponds to A. Yeah, A is H. A is H, right? Yeah. And B is F. B is F. And between C and D, which one is?
Time. I'm not even going to let you know what the right answer to this is. I don't even care. Yeah, exactly. Yeah. Instead, I'm just going to give you a different question. This is another way of getting at that same piece of reasoning. Now, this is a fairly sophisticated task. I'll be honest. We develop tutorials. And you'll see examples of tutorials. Lillian spoke last night about the development of tutorials. We do the same thing in astronomy. And our tutorials in astronomy have a very particular wrapper that they're confined to, and that is they have to work in the lecture setting with 100 students and 15 minutes. So this is like the culminating part of a tutorial. I've just broken a tutorial apart, if you will, into think, pair, share questions and showed it to you. The actual tutorial itself has other questions along the way that guide students' discussions more structured so that you don't miss any piece. And embedded in it, in the tutorials, are student debates, where two students might be debating about the exact same thing you guys are debating. And as students in my class, they're asked to read these student debates as part of their tutorial and be confronted by what might be their way of thinking that is incorrect still, right there in real time. You're going to do another tutorial in the next session on finding extrasolar planets, but not using the Doppler method. There's another method that I want to teach you about for finding extrasolar planets. I just wanted to show an example of the level of task that you can accomplish in your normal everyday classroom using a curriculum that people have already developed. You don't have to do the heavy lifting. I'm just trying to give you an example of this. But I do have one more question I want to do with you, but I see that you have a question first.
Yeah, I noticed going from, say, the concepts to actually doing some kind of maybe
Application, yeah.
Right. I found myself wanting to disengage from conversation to actually try
And think on your own about it. Yeah, yeah. I think that this does happen. I think that there are many, many different modes that we go into when we're confronted with different kinds of content. And I'm not too different from you in this regard. Sometimes I feel like could I just have 30 seconds to think about this on my own before I have to explain it with you? But what we find is that even when we're forced to start that conversation, the same ideas we wanted to think about on our own are sometimes both more robustly discovered and thought through while talking to somebody else. And sometimes we get pieces of information we needed in that discussion with the other person that we might not have stumbled upon by ourselves when we thought about it in isolation. But there is sort of a social, cognitive desire to want to be able to think about it by ourselves. And I'm not saying it isn't valuable and it shouldn't be allowed, and it's certainly what homework's for and all the other things. This is also valuable, is I guess what I would say. And I know that it's frustrating. And I have students in my class who say, I don't want to work with anybody. And I don't fight them, because they could have a gun. I live in Arizona. I don't even know what else to say. They scare me, okay? And I don't want to get in a fight about that. They could be right? And I don't want to make that kind of choice for them or with them necessarily. What I do say to them is, these activities were structured for you to work with a partner, and you may find that it's much more valuable in the long run if you do that. And so I'll let them work on tutorials by themselves for the whole semester if they want to, but here's what my statistics show. That's 1 in 100 at most. But I don't want to fight it either. I think that it's valuable to let people be that way. So I think that's a very valuable question. And I think we represent a group of people that may be biased that way also. We might be people that like that more than others, and I see some nodding going on. Like, I don't like talking to people. Our research even shows something interesting about this. When you look by major at which populations benefited most from interactive teaching methods in the gen ed course, you might have thought that the science majors had the highest learning gains. They didn't. It was the arts, humanities, and social science students who had the highest learning gains because they're willing to talk to each other. And they benefited most from it. Something to think about. I'm going to do one more question, and then I'm going to take questions because I have just enough time. I'll just take questions from everybody. So let me just do one more with you. Do not talk to your neighbor. Do you need more time? Okay, let's vote on 3. 1, 2, 3. That's a rainbow. Truly a rainbow. I love that. Okay, anyway, I'm not going to even tell you the right answer, let you talk to each other. I have to move off this question. You'll keep trying to solve it. Okay. Any questions before? In the next hour, you will go into breakouts, and you'll rotate through different breakouts. One of the breakouts you're going to do are going to be with Gina and I working more on how to use learner-centered teaching strategies that goes towards doing an actual activity that's in one of the tutorial books. So you'll get to see a more rich example of it, and I'll show you some examples of data while we're at it. But I just want to answer any questions you all might have. I'm going to start over here. Yes?
It's the same question I had before. Do you ever not give the students the right answer?
Do I ever, too many negatives, do I ever not give students the right answer? I always help the students understand whether there is a right answer or not in the room and what percentage-ish it's at, if that's what you mean. Like, when I say most of you, I would have socialized my class. No, you automatically know it's more than 70%.
No, you just didn't give us the answer.
Do I ever just move on and say, no? Because I don't care if you guys are learning the astronomy. I care enough. In fact, every single one of these questions is foreshadowing a question that will be on my exam. There will be an example of this on my exam. That's part of the nature of implementation that I don't think it's talked about enough here. Is your students really care about their, oh God, I got to change it, really care about their grade, right? Really care about their grade. And they should. They're paying for it. You know, it's part of their future. And they want to know what's going to be on the exam, really, really want to know. And you'll get this question from them, maybe you already have, like, what's on the, how do I study for the exam? How do I know what's on the exam? Out of everything we did, what's on the, so having ways of chunking information to help them know, that's an example of something that's going to be on the exam, like that, not exactly that. I mean, to do this again and have it be authentic, all I have to do is move this dot anywhere. And it's a new, change this direction, move these dots, whatever I want, and it's a new question that's still robust, has high differentiation amongst students who do and don't know. Reasonable difficulty. So I tell them the answer, but I do want you to know that I'm foreshadowing exam by what I'm doing in class. There was another question at this table? Yeah.
You're pointing your finger to your slide. Were you
While you guys were looking at the question, I was acting like I've never seen it before, and I was reasoning it out too. If you don't feel comfortable doing that and you think it looks silly, don't do it. But what it does do is it suggests to the minds of my students that this is a valid, reasonable, difficult question that even I have to reason through every time I want to remember what the right answer is. So it's an interesting thing that I do that I see profit from. Yeah?
So I see that you dig deeper and deeper, right? So is that the final point that you can get to is the level of the difficulty you're going to test on? I mean, for different student groups, maybe, I mean, you can kind of probably stop at a different point, right?
And I think that what you've noticed here about how the questions are getting more complex, more intellectually rigorous, involving more and more reasoning steps, requiring more and more of your application of all of the little pieces in a right way or you have no chance at it, that becomes the goal of my class. Can your ability to think about the physics get to a really sophisticated, almost expert-like level, and how can I scaffold a set of things that will bring you there and let you know along the way whether you're coming along and still succeeding by giving you enough checks during the middle of all of this that you may not even have to talk to each other because you're all getting it right. That's fine with me. In fact, it makes your students go, yeah, I got it. I can do this early on, and then they end up, crashing and burning at the end, but that's okay. Other questions? Yeah.
Yeah, when you're doing this sort of lecturing by filling in the blanks side of thing, I can envisage, this may not be a problem for large classes, but I envisage like a few keen students will leap in there and the rest will sit back.
I'm glad you asked that. There is a minimum size class for which that doesn't work. And I would say somewhere where most of you raised your hand that you teach classes of 25, that climate's tricky. And you have to be careful at whether you call on people or not, how you might ask them to answer out loud or not, is really, really a tenuous scenario. So I think it's good that you brought that up. I probably wouldn't do a lot of fill in the blank every day, all the time with a class that small, but I still do it. Yeah, but you have to be careful about knowing, and I'll tell you one easy way to adopt it. If you really want to experiment with it, try it as a 50-50. Will it be more or less? Will it be hotter or colder? So when you stop, you're at a place where you're like, is this a time, damn it, is this a time when it was moving toward or away? Rather than saying, how was it moving when it was at that time? So that's one way to start making these chunks as 50-50s, much more easy to do. In the next section, I'm done. We're going to move away from looking at how the radial velocity method works, which is all of these blue dots. And I'm going to teach you how all the green dots happen. These are all extrasolar planets that have been found. And I want to teach you the method for all the green dots next, which is a whole different technique that involves a whole lot more difficult physics. Thanks, guys. Yeah.